welcome to the UGC lecture series. This is the EPG Pathshala lecture series on the subject of computer science. We are talking about the paper machine learning, and in this module we are discussing neural networks. This is the second module on neural networks. We had already given a basis and the foundations of neural networks in the last module. These are the people responsible for the development of this particular module, and these are the learning objectives of the module to explain backpropagation learning method for a feed forward network. So, we had just seen the basis of feed forward network in the last module. So, we are going to look at backpropagation learning, a new method of learning that we have not discussed till now. Then we are going to discuss regarding overfitting of neural networks, and also we are going to touch upon Bayesian neural networks, and then we are going to look at application, both a real time application and a common application of neural network. Some of the keywords that we use here are backpropagation, regularization and applications. So, let us look at error backpropagation. Most training algorithm uses an iterative procedure for error function minimization. You remember we started by saying in the previous class that we are talking about error, minimizing the error. So, we are talking about training is basically about minimizing the error between the output we get and the expected output. So, each iteration involves two steps. One is the evaluation of derivatives of the error function with respect to the weights. Remember, how do we change the output to suit what we want? We change the weights. So, the first step is the evaluation of derivatives of the error function with respect to the weights. And the second step is you propagate these error backwards in order to evaluate the derivatives, and then second step is use the derivatives to compute the adjustments to be made to the weights. So, evaluation of derivatives of the error function with respect to the weights, propagate the error backwards again to evaluate the derivatives, and use these derivatives to compute the adjustments that you need to do to make to the weights. So, this is the basis step of error backpropagation. So, backpropagation terminology, goal is the efficient technique for evaluating the gradient of an error function E of w for a feed forward network neural network. So, backpropagation provides a computationally efficient method for evaluating such derivatives, okay, that is the error gradient. In subsequent stages, weights are adjusted using these derivatives. So, what do? We use weights to find the derivatives, then we try to minimize the derivatives by adjusting the weights. So, achieve using a local message passing scheme. Information is sent forwards and backwards alternatively. So, now we have a method where the feed forward network has changed, where the signals goes now in both directions. So, the overview of the backpropagation algorithm is as follows. You choose the initial weights randomly for the network, okay. Feed in a training sample and get the result. This is a normal feed forward. Then calculate the error for each node starting from the last stage to the input node, that is the backpropagation, and then update the weights accordingly and repeat with other samples until the target output converges. Now, let us just discuss this a little more in detail. What are you doing? This is very interesting because we are starting with random weights. So, you choose the initial weights randomly, which let us assume 3 layers here. So, input, hidden and output. So, you start with random weights, you have 2 weights, right. So, you start with random weights throughout, feed in a training sample and get the output. So, this is basically what we do for a feed forward. Now, you calculate the error for each node starting from the last stage and to the input node. So, you go the other way around. Now, this is the input, acts as the output, acts there, and then you go back. Update the weights accordingly and repeat with other samples until the target output converges correctly. So, this is the overview of the backpropagation algorithm. How to divide up the errors needs a little calculus. Now, evaluation of the derivative En with respect to the weight Wji by a chain of partial derivatives. So, what we do here is this is the Zi Wj, this is the output. So, it defines the delta j and this is the activation function. So, we have delta Aj by delta Wj is equal to Zi. So, substituting that value in delta j xi, thus the derivative is obtained by multiplying value of delta for the unit at output end of weight by value of z for unit at input end of weight. So, you need to figure out how to calculate this delta j. So, this is the major problem. This is the evaluation of the derivative En with respect to any weight Wj. So, the error backpropagation algorithm works the same this way. You have an unit j and you have a unit k. The backpropagation formula is delta j is equal to, that is the previous one, you are going back, is h dash of aj w kj delta k, okay. So, from the unit k. the value of d for a particular hidden unit can be obtained by propagating the d's backward until from units of higher up in the network. So, you are propagating it backward and apply the input vector xn to the network and forward propagate through the network using the normal activation function and the evaluate the delta k for all output units, and then that is your expected value is Tk and your your output value is Tk and your expected value is Yk. So, you find out the delta, back propagate these using to obtain delta j for each hidden unit. So, now you are back propagating it. This is the next h of h dash of aj that you use for the back propagation, and use this derivative of this error by the weight equal to delta j zj to evaluate the required derivative. So, this is what we are trying to do is we are taking it forward, finding a target value, using the difference between the target and the expected values to find the error. Then we are evaluating that first, and then we are propagating the deltas to obtain the delta j for each hidden unit backwards from the output to the backward, and then we are using the derivative to evaluate the values. So, let us see an example of a simple example of a forward and backward propagation. Consider a 2-layer with a sum of squares error. The output units have linear activation function and hidden units have logistic sigmoid activation function. For each input in the training unit, the forward propagation is this way and z of j is tan h of the activation function. So, delta is equal to 1 minus xj squared and the weight of the output. So, backward propagation deltas for the hidden units. So, this is h dash a is equal to 1 minus h a squared, that is because we are assuming sum of squares error, and derivatives with respect to the first layer and second layer weights will be like this. This is the derivative for the first layer of weights, and that will be the input to the hidden. The next one will be for the hidden to input, and the next one will be for output to the hidden layer. So, you update the weights accordingly depending upon the values of the derivative of the error. So, this is what we do in the simple example. So, what are the strengths and drawbacks of back propagation? The strength is it has got great representation power. Okay. Many such functions can be learned by back propagation learning. Widely applicability of back propagation learning, and only requires that a good set of training examples are available. You do not do anything else, you are giving random weights. So, weight determination is not a problem. You start with random weights, get a good set of training samples. Remember, we started with that, went, came back, took another sample and so on till the weights became stabilized or converges. So, no prior knowledge or deep understanding of the domain is needed. So, you can use this for ill structured problems. Tolerant to noise and missing data in samples because it is graceful degrading. Easy to implement the core of the learning algorithm, not very difficult to implement. Good generalization power, accurate results of inputs outside the training set, because we are using this and changing the error. So, even if you give other input data, it is, in other words, it is not overfitting. And the drawbacks are cannot escape from the local minima error state. So, that is there. We are trying to find an error, you may land up with a local error, not the global error. So, the overall global error reduction may not be there. Not every function that can be represented can be learned. So, this is another problem. You can land up with a dead end, you may not learn the function. So, these are the strengths and drawbacks of back propagation. Now, let us look at the network parameter selection. How do we select the network parameters? A good network model requires more than the core of the learning algorithm, it requires much more than that. So, what do you need? The learning accuracy, speed and generalization is highly dependent upon a set of learning parameters. What all? Accuracy, speed and the generalization. So, initial weights chosen at random for the hidden layer and then normalize the weights. Training sample must be good representatives of the problem space. If this is not true, this is true for most machine learning algorithms, especially true for this backpropagation network. Number of training samples as a thumb rule for W weights and E desired error rate, we need at least W by E samples. So, at least that much samples should be there. Number of hidden layers is problem dependent. So, that is not, you cannot choose that. Number of hidden units, layers, that is layers. Remember, number of we have seen almost all the examples we had only one hidden layer, but we chose m. M is the number of combinations you have. So, the number of hidden units for n input units we need 2n hidden units for binary data and much greater than 2n for real data. So, that is a thumb rule. Most parameters you cannot decide and say this is the parameter, it is normally determined empirically. So, what all should you do? The initial weights, they are normally chosen at random. The hidden layer also you after that you normalize the weights. Training samples must be good and must be representative of the sample space. The number of training samples also, as a heuristic we say, if W is the weights and E is the desired error rate not error rate, then W by E is the number of samples required. Number of hidden layers we do not know, it is problem dependent. Once you decide the number of hidden layers, how many hidden units do you want in each layer? That is the for just one hidden layer, if you have input units require 2n hidden units for binary data. So, twice or greater than that for real data. Most parameters you can just give the heuristics, but it has to be determined empirically by doing experiments and seeing what the output is. Now, we will go to another topic connected with this, which is called as regularization. So, what is this regularization? In machine learning and statistics, it is usually used for model selection. It actually introduces additional parameters or additional information to prevent overfitting or to solve the ill-posed problem. We had this issue already when we spoke about support vector machines in the last previous modules, where we spoke about introducing a variable in order to slack variable in order to take care of this problem. We did not want underfitting, we did not want overfitting. So, you must avoid overfitting, because then actually if you do exact overfitting, no learning happens. So, you introduce additional information to avoid this overfitting. So, it penalizes models with extreme parameters. So, there is restrictions for smoothness, bounds on the vector space form, all these it penalizes models that have these problems. Okay. Theoretically attempts to impose Occam's razor on the solution. Remember what is Occam's razor? Occam's razor says that given a data space, try to find a hypothesis which is the most simple. So, it theoretically it attempts to impose that Occam's razor on the solution, make it as simple as possible. From a Bayesian point of view, it corresponds to imposition of prior distribution on model parameters. Remember the Bayesian network, we have just touched upon it. You have prior probability, likelihood. So, you try to bring in some prior probability so that your space is a little bit restricted by putting an imposition. Least squares method is a very simple form of regularization. So, regularization, you can do regularization by determining the number of hidden units. So, the number of input and output units in a neural network is determined by the dimensionality of the data set. That is not in our hands, it is determined by the dimensionality of the data set. Number of hidden units m is a free parameter and controls the number of parameters, weights and biases in the network. So, the number of hidden layers and hidden units, okay, hidden units in each layer. So, the number of hidden units is a free parameter and it controls the number of parameters, weights and the biases. Remember Wj of plus W0. So, that in the network, it is adjusted to get the best predictive performance. So, possible approach is to get maximum likelihood estimate of that m, the number of hidden units, which gives a good generalization procedure. So, which means you try it for different values of m and try to find the one that gives the best estimate. So, that is the regularization using hidden units determining. Another one is using simple weight decay. Generalization error is not a simple function of m due to the presence of local minima. We had local minima. So, you need to control the network complexity to avoid overfitting. That is what we were doing, that is the regularization. So, you choose a relatively large m and control complexity by adding a regularization term. So, have large m, do not reduce m. Simplest regulator is weight decay. So, you have a weight decay which will reduce the weight as you increase the number of units. Effective model complexity determined by the choice of the regularization coefficient lambda. Regularizer is equal to a 0 mean Gaussian prior with the weight vector, it is equivalent to that. So, another method of regularization is by early stopping. Simple weight decay is inconsistent with certain scaling properties of the network mappings. So, early stopping, alternative method where the error is measured with an independent validation set, an error decreases as first followed by an increase in the network as the network starts to overfit. So, you will know that. So, you just try to do an validation, and normally the error will decrease at first and it will start increasing as the network starts to overfit. So, training stopped at the point of smallest error with the validation data. So, if you have that curve, it will decrease and after that it will start increasing. So, at the point it decreases, that time you stop the training. So, there is a desirable invariance property associated with the regularizer. So, in pattern recognition, prediction should be unchanged or invariant under one or more transformations of the input variables. This is an invariance property. So, for example, in the classification of handwritten digits for an object, the classification should be assigned irrespective of its position within the image, which is translation invariance, or the size of the image, which is scale invariance. The classification should not be affected by the position in the image of the object or the size of the object. So, the one is called translation invariance and the translation invariance, and the other is called as size invariance. So, there are 4 approaches to learn this invariance: augmenting the training set using replicas of the training patterns, adding a regularization term to the error function. Okay. See, when you do, you try to reduce the error the maximum, you are actually overfitting. So, you add a regularization term so that there is still some error there and here. Extracting features that are invariant during pre-processing, that also you can do, and build the invariance properties into the structure of the neural networks. This is just to tell you that when you are doing this classification, you need to consider these aspects. Then there is a topic called mixture density networks, general framework for modeling conditional probability distributions. So, the goal of supervised learning is to model the conditional probability P of t by x, that is the posterior probability as you say. In practical practice, actually problems distribution can be multi-model, particularly in inverse problems. So, what you do is, in such cases the Gaussian assumption can lead to poor results. So, in regression is typically assumed to be Gaussian. So, what you can do is, you can use least square corresponds to maximum likelihood under Gaussian assumptions. It leads to poor result for highly non-Gaussian inverse problem. So, modeling conditional probability distribution is achieved by using a mixture model for the conditional probability. So, here you can use forward problem data, x is sampled uniformly, target is by another function. So, here red curve is result of fitting a 2-layer neural network by minimizing the square of the error, corresponding to inverse problem by reversing x and t. So, you can do that also. So, here you have 2 things that you want to 2-layer network. So, you can change the order and use this. So, it is very poor fit to the data, but it will give you a good problem. So, model with k components, continuous variables, Gaussian, binary variables, you can have use Bernoulli also. Note that mixing the coefficient phi is dependent on x and sums to 1 for each x. So, there you have pi of x. Also mean and variances are dependent on x. An example of a heteroscedastic model, since variance is a function of the input variable x. So, this is that variance does not remain constant, it keeps changing. So, that is the idea. The parameters of the mixing model are mixing coefficients, we are bringing in a new coefficient, means and variances governed by the outputs of a neural network with x as input. A single network predicts the parameters of all the component densities. If there are L components in the mixture model and k components where there are L outputs, then there are k plus 2 into L outputs instead of the usual k. So, you are increasing the number of outputs you need. So, this is the network. Network represents a general conditional probability density P of t by x by considering a parametric mixture model. It takes x as input and provides the parameters of the distribution output. In effect, it specifies the distribution and takes x as an input vector. So, this is how you get that variable. So, why do you go for Bayesian? More complex models fit data better, but generalize poorly. Okay. Linear with 2 free parameters, quadratic with 3, cubic and 4 with 4, what happens? So, Occam's razor says that unnecessarily complex models should not be preferred to simpler ones. That is the fundamental of Occam's razor. Neural networks are popular, but notoriously lack objective grounding. That means it does not have that. So, Bayesian approach allows different models to be compared, network with different number of hidden units. Then you compare, you find which is the probabilistic one better, probabilistically better. So, the difference between classical and Bayesian is classical neural networks use maximum likelihood to determine network parameters like weights and bias. Regularization maximum likelihood is map maximum A posteriori regularizes the logarithm of prior parameter. Bayesian treatment marginalizes over distribution of parameters in order to make the prediction rather than distributing over the weights and biases, okay, using maximum likelihood. So, there is a need for approximation in Bayesian treatment. In simple linear regression problem under the assumption of Gaussian noise, posterior is Gaussian and evaluated exactly. Predictive distribution is found in the closed form. In multi-layered, you have highly nonlinear dependence of network functions on the parameter values, and exact Bayesian treatment is not possible. So, you take the log of posterior distribution is non-convex, implying multiple local minima of the error functions. Approximate methods are therefore necessary. So, we go in for approximate methods. So, there are two approaches to the Bayesian treatment: variational inference using a factorized Gaussian approximation to posterior distribution, and Laplace approximation. So, here we are talking about the approximation techniques that they use, and involves two approximation: the replacement of the posterior by a Gaussian centered at a mode of true posterior. Covariance of Gaussian is small, so network function is approximately linear. Using the above framework, we can compare alternative models with different number of hidden units. The basic thing of Bayesian is that you take different models with different number of hidden units and see which is better. To decide which is better, you use the Bayesian treatment. Now, let us go to some applications. Now, artificial neural networks, there are many applications. We are just taking two. The first one we are taking is pattern recognition, very important application of popular application of artificial neural networks or neural networks, reading zip codes. So, signal filtering is the reduction of the radio noise, data segmentation detection, this is another application, data segmentation detection of seismic onsets, data compression, T-wave image transmission is required, database mining, marketing, finance analysis and so on. So, these are some typical applications of artificial neural networks. Adaptive control for vehicle guidance. If you see, many of these applications are very valid in today's scenario. So, let us first take the application of a ANN vehicle steering application. So, here you have the vehicle steering. So, remember that is for adaptive control. So, autonomous vehicle is an example system that uses ANN to steer a vehicle on a public highway. So, this is a 13 to 32 grid of pixel intensities are available, and output you expected the vehicle's steering direction to be given. So, how do you do this? This is an example. The network architecture consists of the number of input units is the number of pixels that you use to represent the grid of intensities. The number of hidden units used are 4, the number of output units used are hidden units, 1 hidden layer, 4 hidden units, and number of output units used is 30. So, each hidden unit has 960 inputs and produces 4 outputs connected to 30 output units. That is what the meaning of this, and each output unit corresponds to a steering direction. So, number of output 30, each of the 30 corresponds to a steering direction. So, weight of the inputs prefers left turn, weights from hidden unit to 30, and these are the learned weights. Weights from hidden unit to 30 prefers the left turn, weights to input units to one of the 4 hidden units. White is positive, you can see here, black is negative. Size indicates the weight magnitude. So, this is the application. The next application we are going to look at is the ANN character recognition. Optical character recognition system were the first commercial systems that were available using neural networks, and this is a demonstration of an application of a multi-layer feed-forward network for printed character recognition, not for the other one. The task is recognition of digits from 0 to 9. Each digit is represented by a 5 into 9 bit map. The commercial applications use a 16 into 16 bit map. Here, for simplicity's sake, we are doing this. So, this is the, if you look 9 into 5, that is 45. So, here you have the bit maps for the bit recognition. So, each digit is represented by a matrix of 49 into 5. And what do you do here? Architecture, the number of neurons in the input layer is equal to the number of pixels in the bit map. Hence, there are 45 input neurons. The output layer has 10 neurons, one for each of the characters to be recognized. This tells you how to design the neural networks also. Number of hidden neurons is varied. You keep varying the number of hidden layer. Here also he uses only a single layer. You keep varying it and experiment it till you get the appropriate output. So, here the neural network, you have so if you see here, it is taking those 45 cell positions and saying whether it is a 0 or 1. I will just show that to you. So, here you have 0, 0, 1, 0, 0, 0, 1, 1, that is what it is showing here, 0, 1, 1, 1, 0 and so on. And so, you have 45 input units, here they have shown 5 hidden nodes and you have 10. So, these two are fixed, 10 is the number of. So, here if you see output, you will have that the first number is 1. So, 1 to 9, 1 to 10. So, you have here 1 to 10, and if it is 2, that is what is recognized, then you will get 2 as the 1 as the output for only 2. So, the application of learning curves, you can have 3 layer, that is 2 hidden neurons, 5 hidden neurons, 10 hidden neurons and 20 hidden neurons. Different values are given and the number of epochs is done, and he is calculating sum of squared errors. In order to see, you see 1 it gives like this, 2 like this, 5 and 4. So, you want the errors to be the least. And the performance evaluation, the noise level and the regularization error, you will see that for 5 you have different 2, 3 and 4. Okay. And this is the noise level and the recognition rate. So, you will see that the recognition rate is trained with perfect examples and trained with noisy examples, which is again important. So, a neural network is as good as the example used to train it. This is true for any machine learning algorithm. Hence, the digit recognition learning can be improved by feeding the network with noisy examples of digits from 0 to 9. The performance evaluation of the network trained with noisy examples will improve it, which we saw. And the recent advances, the introduction or integration of fuzzy logic to the neural networks, pulsed neural networks, where the communication happens through pulses and use the timing of the pulses to transmit information and perform the computation. And hardware specialized for neural networks is also becoming popular, where you directly encode the neural networks onto the chips or specialized analog devices for increasing the speed. So, the summary is we explain the backpropagation learning method for a feed forward network, where we use the error and the local and global minima, and we propagate it. So, you start from input hidden to output, then you use the output to hidden and hidden to output by varying the weights. Here you start with a random weight. Discussed about reducing overfitting of neural network, and we also introduced the concept of Bayesian neural networks, where we try to use that error to find out which is the best set of weights that we need to use. Then we discussed a real time application of the vehicle steering. We also introduced a common application of neural network, which is very popular, which is the application of for character recognition, printed character recognition. So, this is what we discussed in this particular module. Thank you.